Modern web architecture traps user data inside application-specific back-end databases. Your images live on their servers, governed by their internal terms. The decentralized web node, or DWN, provides a different architecture. It is a personal data store anchored to the user rather than the application provider. You decide where it is hosted and who has access. In this model, applications become stateless. As we see in this animation, the central DWN holds the data, while distinct application nodes orbit the hub, pulling information in rather than storing it locally. The DWN acts as a standardized message relay and synchronization mechanism. The node is reached and managed using a cryptographic string known as a decentralized identifier, or DID. To understand how a system operates without a central server, we are going to deconstruct a decentralized image sharing app. We will trace the path of a photo from upload to retrieval, examining the record's interface, protocol definitions, and the cryptographic message signing required for each interaction. This shift in data ownership dictates how developers must build, requiring a precise understanding of the underlying node mechanics. Before our image sharing app can read or write a photo, it faces a technical hurdle, locating the user's DWN without a central directory. Resolution begins with the user's decentralized identifier document. This animated diagram shows a typical DID document JSON payload. To find the physical node, the application parses this document to locate the service array. Within that array, the app scans for an object where the ID is tagged exactly as #DWN, and the type is designated as decentralized web node. The service endpoint URL array inside that object provides the exact web addresses required to route traffic directly to the user's node. Further down in the document, we find the ENC and SIG properties. These represent encryption and signing key identifiers, mapping to the public keys required to establish a secure cryptographic channel with the node. The DID document acts as the DNS of web5. It mathematically routes requests to the correct decentralized data store, ensuring the application knows where to send data before any exchange occurs. Once the app locates the node, it needs a way to communicate. The records interface provides the universal standard for all data interactions and CRUD operations on the DWN. Web5 ignores proprietary SQL tables. Instead, DWN data is stored as logical records, validated against explicit, publicly readable JSON schemas. Developers structure these payloads using standard IDONA media types. A profile update might use application.json, while a photo uses image.jpg. When our app needs to display a user's gallery, it sends a records query message. This abstract diagram shows the app transmitting that JSON message to the DWN, with the filter object expanded to reveal the specific matching criteria. The DWN uses the schema URI property within that filter to ensure it only searches for and returns image data, filtering out text posts or contacts. To pull a deterministically linked set of objects, like fetching all the comments attached to a specific parent image, the app uses the context ID property. The records interface provides a standardized API for all data. Developers no longer write custom backend database queries for every new application. They simply pass standardized JSON messages to the node. Without a centralized backend, the DWN needs a mechanism to enforce rules and prevent apps from writing incompatible data into a user's storage. The solution relies on protocol definitions. These are declarative JSON schemas that set the rules for data hierarchies and interaction patterns. We can examine the requirements for our app by looking at the specific image sharing protocol. This visual representation divides the protocol JSON into two main blocks, types and structure. The types block strictly restricts data formats. The node will automatically reject any file that is not a JPEG, PNG, or GIF, maintaining data integrity at the edge. The structure block enforces hierarchical rules and payload limitations. Here, the node sets a limit on file size, rejecting any image larger than 500 megabytes. These protocols also manage security through role-based access control, dictating which actors can interact with specific data types. The DWN owner can assign a writer role to specific external actors, like friends or collaborators. The protocol defines the exact permissions for this writer role, granting them the ability to create, update, or delete their own images on the owner's node. Conversely, the owner can assign a viewer role. The node mathematically restricts viewers to read and query operations, preventing unauthorized modifications. Protocol definitions eliminate the need for application-side validation. Data governance and security reside with the user's personal node, which rejects any request that violates the contract. Even with strict protocols, the DWN must ensure message integrity. It needs a way to prove a write request actually came from the authorized user. The network solves this by requiring cryptographic signatures for any message that requests an authorized action. As shown here, the first step of this process passes the JSON message descriptor through a cryptographic hash function, outputting a unique alphanumeric string known as a content identifier, or CID. This CID is then signed by the sender's private key, wrapping it into a general JSON web signature block labeled authorization. If a message arrives lacking a valid JWS that mathematically matches the required decentralized identifier, the DWN natively rejects it. Beyond message integrity, protecting the payload content requires a dual-layer encryption model to ensure that data remains inaccessible to anyone but the intended recipient. In the first layer, the local node generates a symmetric key. This key encrypts the image data payload, turning the photo into unreadable ciphertext. In the second layer, that symmetric key is encrypted asymmetrically using the recipient's public key, derived via an HMAC key derivation function. Neither the network hosts nor the applications relaying the traffic can alter or read the private data, without the explicit cryptographic keys held by the participants. A single personal node provides autonomy, but relying on one physical device introduces a single point of failure. To guarantee data availability, the architecture replicates the user's state across multiple synchronized DWNs. This diagram illustrates a local device node, like a laptop, interconnected with a remote cloud node, both displaying identical data record counts. This mesh enables offline-first capability. If internet is lost, the app writes images directly to the local DWN memory. Once connectivity resumes, the sync interface takes over, propagating a sync message payload from the laptop node to the cloud node to reconcile state. The nodes compare their cryptographic message histories, detect the delta, and automatically replicate the missing files and payloads across the mesh. Synchronization ensures high availability. It turns personal laptops and mobile phones into resilient, autonomous edge servers that collaborate to preserve the user's data. The mechanics powering this image-sharing app represent a broader blueprint for decentralized storage. This constellation shows how different applications, from music to productivity, connect to standardized personal nodes. Decentralized web nodes form a data mesh, utilizing standard JSON schemas and cryptographic routing to replace back-end servers. Applications in this ecosystem are stateless. They no longer maintain internal user silos or proprietary databases. Applications must request access to the user's data according to the logic defined in the protocol. This architecture transfers power from platform aggregators back to the individual developer and the end user. It removes platform lock-in. Developers can build front-end experiences without the financial burden of managing back-end data compliance or server infrastructure. The DWN specification provides the infrastructure for a user-owned web, treating identity and data as an inseparable, secure, and universally portable asset.